Hello, this is Concrete Path, and the lecture here is to, to go for the losses of the pre-stressed concrete beams. The other losses we have for the pre-stressed beams, pre-stressed concrete beams. Let's go. Here, one of the losses is that we have anchorage loss, anchorage slip, anchorage slip, and this is under the category of immediate. This is that immediate loss, immediate loss. Okay, it's not a time dependent loss, so this one is your anchorage slip, and this is observed in post-tension pre-stress concrete beams, post-tension members. Okay, post-tension members. So there is actually a slip of the steel wire. There is slip of the steel wire uh, at the wedge, over the wedges, I can say, over the wedge during the time of pre-stressing, or we can say during the time of anchoring, during the time of anchoring the wire, during the time of anchoring the wire. So this is your loss, that is anchorage slip, anchoring the steel wire. Okay, so this means that you are having that pre-stressed concrete beam, there was some cable, attached, and let's say this side is fixed, and that means this is anchored, and from the other side, when we apply that tensile stress, you apply that pre-stress from the other side. So that means you elongated that wire by some delta. Let's say the elongation was you elongated the steel wire by some 20 millimeters. Now once we have elongated the wire, after that there's a need to anchor the wire such that pre-stress would remain there. That means we should have the effect. We should make sure that our steel wire is at the location when we applied the elongation. So now it should remain at the final location where we have elongated it to. So I would say if the length it has attained now, that is some length of L plus 20. I would say this is L plus 20 length. Now I want that it should remain fixed here. I want that it should not go anywhere. So when I anchor it this side also, so when I'm going to anchor this side now, because of some mechanism, I'm going to anchor this side also now. Initially this side was already anchored. From this side I want to anchor it now. So there is some delta developed. Now I want that it should not lose any of these delta. I want that it should not lose any delta. But at the time of anchoring, at the time of fixing the wire, there's possibility that it might slip, the steel wire might slip back a little bit. So that little bit slip of the wire over the wedge, that's over the mechanism wire from which we are fixing the wire. So if there is some loss, that means a little bit of slip would be possible. That's possible. That's because not each of the process is not 100% efficient, so there might be slip of that wire a little bit. So that little bit of slip during the time of anchoring the wire, that we can call that as some delta slip. We can write that as some delta slip has happened. So I would say, what is the stress that is lost in the steel wires? That is some strain developed because of that delta slip by total length of that wire into that modulus of elasticity. So this is your loss of stress because of that anchorage slip. So at the time of anchoring the wire, you are losing some deformation in the steel wire. You are losing some deformation. You are losing some delta. So that's your anchorage slip, and it is observed in your post-tension members. It's observed in your post-tension members. Okay, post-tension members. And we would say that if you talk about now long member versus short member, if I compare with long versus short member, that means one of the member is having length or more. Let's say here the length is 10 meters, and here the length is what you can call, this is 4 meters. Let's say this is 4 meters. Length here is only 4 meters. But I would say once I am fixing that steel wire from one side, this side I have fixed the wire. Now when I anchor the other side also, let's say the slip is there, and the slip is a function of this anchoring mechanism that we call as anchorage system. So your slip is a function of anchorage system. So to a particular system, that is fixed value. So that value is fixed. It is not function of length. So that value is fixed. So your slip, I would say your slip is a function of, it's a function of anchorage system, that total deformation by the anchorage system, that is fixed here. So but the length, if I keep the length of one wire as 10 meters and the length of another wire as 4 meters, that means this is your short member and this is long member. I want to say what is the loss of stress here. Let's say this deformation, that is slip loss, is 2 millimeters, and in this case also delta loss is also 2 millimeters. I would say what is the loss here? The loss here is more, 2 millimeters out of the total 10 meters into that modulus of elasticity. Here the loss is 2 millimeters out of the 4 meters and into modulus of elasticity. So the loss is more in the short member. So I would say your slip, anchorage slip is a predominant, this is a dominant loss. Anchorage slip is a dominant loss. It's a dominant loss in short members. Dominant loss in short members. In the short members. Short members. Okay. It is a dominant loss in short members. Okay. Now I would talk about that. We should go for the problems, and I would say you are different anchorage systems for the post tension members. Like we have one of the system that is we call as Freycinet system, and one more method is there, we call that as Magnell-Blaton method. So in this case we say your slip, that is anchorage slip, is almost that range, it is in the range 4 millimeters to 6 millimeters, and this value means this is a fixed value. So whether if your length is having, if your steel cable is bigger and if your cable is shorter, that small cable, so it does not depend on the cable, it depends on the system itself. So I would say this is dominant in the dominant loss of stress for the short members. And one more is there, Magnell-Blaton, and in this case we say your slip value is almost 8 millimeters. So this is the standard values we have in these systems, Freycinet anchorage systems and Magnell-Blaton also. Okay. Third one here, I would say, well, let's go for the problem we can have related to that. What you can say, anchorage slip. Let's take that problem. Anchorage slip problem. Let's take the problem. So we have here a post tension beam we have, and there is a cable also. Let's say the cable area is, let's say the cable is having that initial pre-stress of 1000 megapascal. Okay, and slip is at the jacking end. We are saying if the slip is at jacking end, how much is that slip? 5 millimeters, and we need to calculate percentage loss of stress, pre-stress, percentage loss of pre-stress if the beam is, I would say, if the beam is having length of 30 meters and if the beam is having length of 3 meters. So we have two different cases. That means one of the beam is short and one of the beam is long. So this is short beam and this is long beam, I would say. Let's take the first case. That this is your beam, simply supported beam, and we are having that what you call, let's say the cable is straight. We don't care about the cable. We say that there is slip at the jacking end, slip from the jacking end. That slip is after when we try to anchor the wire. At that time this slip is happening. So let's say this side is fixed, and from this side when I'm going to anchor that, this is jacking end. Let's say this is jacking end, and from this side we are losing that slip of, that's 5 millimeters jacking end. So here we lose some millimeters, 5 millimeters. Delta slip is 5 millimeters and length was 30 meters, length of the beam. That means length of the cable is also 30 meters, we can say. And there's also given that data for the steel. ES is equals to 2110 kilonewton per millimeter square. Modulus of elasticity for your steel wire. Now I would say, what is the stress loss? I would say the loss of stress is equals to that is strain That is strain lost into, I would say, what is the strain into that modulus of elasticity? Your loss of strain, I would say, that's delta S divided by total length of L into E. S is equals to 5 millimeters divided by total length of 30 meters, 30 millimeters into that 210 kilonewton per millimeter square. So that is the solution for this problem, and this is coming to be equal to if I calculate it in terms of, if we want to calculate it in terms of what you can say, percentage of loss, initial pre-stress was how much? 1000. Initial pre-stress was 1000. Okay, 1000. So from this, can you calculate what is the loss? I would say the loss here is, we can solve it, 210 into 5 divided by 3. This is 35. So 35 megapascal is there. So percentage loss, I would say, percentage loss is 35 divided by total 1000 into 100. That is how much? 3.5%. 3.5% of the total pre-stress has been lost by this anchorage slip of the total pre-stress. Okay, let's take the second part, that if the length is only 3 meters. Second case is there, if the length is only 3 meters. All the data is same, your slip is not going to change. Slip is a function of anchorage system, so slip is going to remain fixed. Slip is fixed. So if the slip is fixed, this is fixed, only the length is going to change. Now the length is only 3000 millimeters. So that means your loss of stress would be 350 megapascal. Loss of stress would be 350 megapascal. So here we can write 350 by 1000 into 100. So that is 35%. Is that 35% of the total pre-stress? So you can see that 10 times difference is there. Total pre-stress. So you can see that there is an effect that there is more loss in short members because of this anchorage slip. Let's take that second. Let's take second problem that. Let's take one more so we can have that. So we have post-tension cable. Post-tension cable is there, and we have that beam is also there, 10-meter beam, and your initial pre-stress in the cable is 1000 megapascal, and we are jacking one end is jacket, one end jacking. Okay, jacking one end. Okay, your slope at the ends is 1 by 24, and the cable is curved. Curved cable is there. That means it would be a parabolic cable. It would be a parabolic cable, I can say. Parabolic cable would be there. Okay, and area of the cross section of the cable. It's 600 millimeters square. And we have also the data related to the friction loss also given. That mu, coefficient of friction at the interface. It is equals to 0.55 in the curve. Mu interface in the curve, that's 0.55. Your wave effect, that's also called as length effect. That we can say this is wobble effect. Correction factor. Wobble correction factor. That is K equals to 0.0015 per meter. And we are saying that during the time of anchoring the wire, there is slip also. So that slip, how much is the slip? 3 millimeters at the jacking end. From the jacking end we have 3 millimeters of slip. Okay, now we need to get the final loss of stress, get the final force in the cable, get the final force in the cable, and percentage loss of stress because of slip and the friction. Get the loss of stress because of slip and friction. So we have to calculate all those two effects, all these, what you can say, two effects, loss of stress because of these two. Your modulus of elasticity, Young's modulus for the steel is 210 kilonewton per millimeter square. Let's try to get the problem. So it's a bigger problem. So I would say you have a beam, 10 meters. 10-meter beam is there. And there's a cable, parabolic cable. Cable is parabolic. Cable is parabolic. Let's say cable is parabolic, and one of the end is jacked. One end is jacked. That means one end is already anchored. One end is anchored. This is anchored end, and from this side we are applying that Prestress of P naught. And after that, this is like, I can say this is jacking end. This end is jacking end. Okay. Theta at the slope at the ends is given. Slope at the ends is given. That's actually theta 1/24. So I can say your theta here is, I can say, I would say by the symmetry theta is same from both the sides. This is some theta. So this is some theta. This is 1/24. And from this side, this is also 1/24. So overall theta would be here. That theta 1 plus theta 2, that is 2/24. 2/24. So that's over. And we have length of 10 meters. Length of 10-meter beam. 10-meter beam is there. 10 meters. 10 meter is also there. Your initial Prestress of P naught. We have 1000 megapascals. Okay. Area of the cross section of the cable is given. We have mu given. We have K given. So we can solve for the, let's go for the first part. That's loss of stress because of the friction. Because of friction. Loss of stress in the steel wire because of friction. That's P naught times Kx plus mu alpha. Your initial Prestress was how much? P naught was your 1000 megapascal. 1000 megapascal. 1000 megapascal. And we have K value is 0.0015 per meter into X. What should be the value of X? The X value is the length between the two concerned points, between the two critical points. X value. So if only one end is jacked, at that time we say X value is equals to L. That's there's loss going to increase from X equals to 0 to X equals to L. So your value of X equals to L, that's 10 meters. 10 meters. Okay. That's 10 meters. 10 meters plus mu alpha. Mu value is given to you. Mu 0.55. 0.55. I would take that as 0.55 into that alpha. Your value of alpha for this condition, that if one of the end is jacked, so your alpha becomes theta 1 plus theta 2. Theta 1 plus theta 2. So that is actually 2/24. That is actually 2/24. We can have that 2/24. So I can solve that. 2/24. Okay. Everything is perfect. That is the total change of slope from end to end. And this is also, yeah, we can have the final loss equals to 61. That means this overall value is coming to be 61 megapascal. Loss of stress because of friction, that is 61 megapascals. Now we need to take that second part, that because of the slip, how much loss is going to happen because of the slip. So I would say because of the slip, there's loss of stress because of the slip, that is 3 millimeters divided by total length of 10 meters into that E value of 210 kilonewton per millimeter square. So you can solve that value. You can get this value coming to be equals to 63 megapascal. So I would say, what is the total stress? What is the final stress, total stress lost? So P lost is equals to this P1 plus P2, 63 plus 61, 63, 61. So that's sum of these two losses, that is 124 megapascals. Now if I say what is the percentage of stress lost, percentage lost, how much is that? 124 divided by total. Initially it was 1000. Initial value of the Prestress was 1000. Initial value was 1000. Okay, and we have to say this is the total percentage we have lost. So that's some 12.4, maybe 12.4%. Total percentage of this much is lost for this post tension beam. 12.4% of that Prestress. And if I say what is the total force lost, what is the P lost? That would be what is the stress loss into that area of the cable. So your loss of stress was 124 megapascals, and your area of the cable was actually, given to you 600 millimeters square. 600 millimeters square, and that is some value of 74.4 kilonewton. This much amount of force has been lost because of those two effects. So that was the end of this problem. Let's take the one more type of loss. One more type of loss, that's we call it as creep of concrete. Creep of concrete. Okay. See, I would say this inquiry slip was not. I said this is only observed in post-tension members. This was only in post-tension members. If we talk about pre-tension, in that case we say there's what you call as those bulkheads, abutments. In those, your steel is already fixed. Your steel wire is already fixed. Then after that, I would say there's no loss in that case of what you call as in that what you call as pretensions, not in pretension. So that inquiry slip is not in pretension members. It's not observed in pretension members. Okay. Let's take that what you call as that second type of loss, that is creep of concrete. That's creep of concrete. And from this type, I would say this is a time dependent. This is under the category of time dependent loss. Time dependent loss. You might be knowing what is creep. What is creep? It's that deformation under sustained load. Deformation under sustained load. Under sustained load. That means load is there, it's not going anywhere, and for some time after that you come back, there is development of strain. That's because of that sustained loading. Even the stress is also constant. Even at constant stress, that is the stress is same, but still we are having some more deformations happening in the system because of some time. Because it's a function of time, or at the constant stress. So it's a function of time, I would say. And we say that its value we have directly, that we denote that creep coefficient. We can write here, we write that as phi. Creep coefficient, that is what is the creep strain. What is the creep strain divided by what is the elastic strain. What is the elastic strain we have, and what is the creep strain we have, and its value we know for different time stages of those loadings, stages of loading. And we say creep value is the function of time. If I come to that at the 7th day of the loading, if the concrete was only 7th day, if the concrete was only a 7 day old, that means your loading on the concrete is at the time at the 7th day of the when concrete has been made. So it's at 7th day. So at that time your phi value is 2.2. If I apply the loading at 28th day, your value is 1.6. And if I want to apply that loading at the after 1 year, that means your phi value is 1.1. Now similarly, if I would say your value of phi decreases with log of time, log of time. And its general equation is that if I want to say let me calculate strain, let me calculate that creep coefficient at any time between 7 day and 28 days. Let's say I'm calculating for that time is 15. What is the creep coefficient on 15th day? What is the value of that? And that is actually equals to 1.6 plus the difference of the 2.2 minus 1.6, and then log of the difference, log of 28 minus log of location where I want, log of 15, and divide by log of 28 minus log of 7. This is the equation we have. Now let's say that how to calculate the creep loss, how to calculate the loss of stress because of the creep we have, how to calculate the loss of stress in steel wire. So I would say this is some elastic strain. We can also call it as elastic shortening in that way. We have studied elastic shortening. We can treat this part as that elastic shortening. We had that concept that loss of stress in steel because of elastic shortening, because of elastic shortening ES, because of elastic shortening, that was some ES. So I said that this is loss of stress because of elastic shortening. That was coming out to be loss of, that is strain loss because of elastic shortening into that ES. Okay, and this strain ES was actually what is the deformation happened because of elastic shortening? That is, what is the elastic shortening we have divided by total length into that ES, modulus of elasticity. That is your loss of stress. So if I substitute here, if I substitute this value, here, that E modulus of what you call as, this is the that is strain. This is the strain because of elastic shortening. So actually this is elastic strain. And if I substitute here this value, if I substitute this value here, I would say your loss, I would say loss of stress because of the creep, is actually your strain because of creep into your modulus of elasticity, your Young's modulus of elasticity for that material. So this is the equation we have. But how to calculate this part of the creep? So for that I have to use this equation we have. So I would say your loss of stress because of creep is equals to 5 times, that is a strain because of elastic, that is elastic strain. This part is the value of E creep. This E creep has been replaced by that 5 times E elastic, and after that we have that multiple of ES. Now I would say, what is this E elastic? Can you tell me what is this E elastic? Can you tell me what is this E elastic? So that's actually that elastic strain, that is actually elastic deformation, elastic strain. This is because of elastic shortening of the concrete. It is because of elastic shortening of the concrete. Now if I say that this part actually is equals to, this part is actually equals to loss of stress in steel, because of elastic shortening. So I would say your final value of loss of creep, final loss of stress because of creep is equals to 5 times loss of stress in steel because of elastic shortening. This is the equation we can have. Now I know how to solve the loss of stress in the steel because of elastic shortening. I know the equation for that. That was actually that loss of stress in the steel because of elastic shortening was actually m times Fc. If you have that equation, that means that was modular ratio times what was the stress in the concrete, and sometimes we write it as average also. Average stress we also write it as. So this is the equation we can write, mFc. And if I finally say what is the loss of stress because of creep, that is equals to m times phi mFc. I can write here phi mFc. So this is the final equation we can have. So this is the final equation. Loss of stress because of creep is phi times m times Fc. While your value of phi is creep coefficient, so its value would be some 1.1, 1.8, some value would be there. So your m value, it's a modular ratio, modulus of Young's modulus of elasticity for your steel by E of for the concrete, and into that stress at the location of steel. It's the stress in the concrete at the level of steel, where we are calculating the loss of stress in the steel. Because we are calculating the loss of stress in the steel at that same location, we are calculating stress in the concrete at that same level. So let's go for let's take that what you call as first problem. For that first problem related to this concept, that we have a beam 100, that's dimensions 120, 300. We have 6 wires. Of 6 mm diameter. Eccentricity is there 55 millimeters from the neutral axis. This is neutral axis, so eccentricity is there. E equals to 55 millimeters. And the P force is applied on the cross section. So your stresses developed would be P by A, and one more is there, top tensile, bottom compressive, PE by Z. So this is the top extreme fiber, PE by Z, extreme fiber stress, that is PE by Z. But I have to calculate the stress at the level of steel. I have to calculate. This is I would say this is P by A, and this is some value of PE by Z into that value of E, where our cable is there. PE by Z into E. Yeah, actually it should be my by I. This should be value of I neutral axis. This is the value of my by I. Okay. Now the problem is that you have this cable. Initial pre-stress we have equals to 1150 megapascal, and creep coefficient is 1.5, and the ratio of modular, and the modular ratio can be solved as ES by EC. That's given to you as 2 into 10 to the power 5 megapascal divided by 3 into 10 to the power 4 megapascal. So that's some value m equals to 7.6. Is it 20 by 3? It's coming to be 20 by 3. So that you have to calculate. I would say this is 20 by 3. This is a modular ratio of 20 by 3. That is 6.67. So modular ratio of 20 by 3. Okay. One more data is provided to you. Yeah. We need to calculate loss of stress because of the concrete creep of concrete. So loss of stress in the steel wire because of creep of concrete. So this is the problem. Calculate that loss of stress because of the creep of concrete. So we have the equation for that. That is actually phi times m times fc. So phi value are already given to you. Phi value 1.5. So we can write 1.5 into m. The value of m is 20 by 3. We calculated that. And fc is the stress value of stress at that location. Value of stress in concrete at the location of the steel wires. So at this location I will have to calculate. So can you tell me what is the P force we can have? Based on the data that initial pre-stress is given to you. Initial pre-stress is given to you, and number of wires is also given to you. 6 wires of 6 mm diameter. That means P force can be solved as initial P naught force is equals to P naught into area of the steel wires. Okay, so I can write that your initial pre-stress was 1150 megapascal. 1150 megapascals into your area of the steel. 6 wires of 6.5. 6 wires of 6.5. So this is your final value. So your P force is coming to be equals to 195.093 kilonewton. 195.093 kilonewton. 195.093 kilonewton. Okay, let's substitute that value here. Let's substitute those values here. Your P value is 195. So we can write here, this is 195, or we can write in, if I write it in newtons, I can write 195.093 newtons divided by area of the cross section is 120 into 300 millimeters square. After that, one more stress is there. One more stress, that's plus PE by Z, that is 195093 newtons into your E square. Into your E square, what is the eccentricity we have? Eccentricity 55 millimeters. 55 square millimeter square divided by the moment of inertia about the neutral axis, BDQ by 12 millimeter power 4. So your stresses at that level, at the level of steel wires, is this sum of these two. So you can solve that, and it's coming to be equals to 7.6 megapascal. So let's substitute that part here, 7.6 megapascal. So we can get the final solution that your loss of stress in the steel wires because of creep, that is coming to be equals to 76 megapascal. 76 megapascal. 76 megapascal. Now let's come to one more kind of loss that we call as that's shrinkage of the concrete. Shrinkage of concrete, and that's also a time dependent phenomena. Shrinkage of concrete. Because of the shrinkage of concrete, we have loss of stress. So this is also a loss of stress. Loss of pre-stress in steel. Loss of pre-stress in steel. Pre-stress in steel. So it's observed in both the kind of beams. The one is your post tension, and one is your pre-tension beams. All those kinds we have observed this phenomena. So your shrinkage results in shortening of concrete. It results in shortening of that concrete, or we can say steel wire also, or steel wire. Once your concrete is going to shorten, so your steel wire is also going to shorten. So based on that we have some shrinkage strain values for the two kinds of beams. So if I talk about that, what should be the value of shrinkage strain? Shrinkage strain I would say this is the shrinkage strain in concrete, because of this is actually shrinkage strain in concrete, shrinkage strain in concrete, ECS. So I would say the loss of stress because of the shrinkage is actually equals to loss of stress because of shrinkage equals to some strain, shrinkage strain into your modulus of elasticity for the steel. This is the loss of stress. Now its value is given to you for the two kinds of materials, for the two kinds of these beams. One is your post-tension beams and one is your pre-tension beams. If I talk about pre-tension beams, we say your total residual shrinkage strain, total residual shrinkage strain, its value is 3 into 10 power minus 4. This is the value of strain we have for this one, ECS, for the pre-tension. And for the post-tension, we have ECS is equals to 2 into 10 power minus 4 divided by log of T plus 2. Log of T plus 2. Your T means what was the age of the concrete at the time of loading? Age of the concrete? I would say age of the concrete at the time of loading, or at the time of transfer, at transfer stage. What was the age of loading at transfer stage? Okay. So age of the concrete at transfer stage, that is the shrinkage strain, 2 into 10 power minus 4 log T plus 2. So we have two different values, and let's take the first one. Let's take the first problem related to this concept. Let's go for that. So we have a problem here. Let's calculate that loss. Let's calculate your initial prestress force of 300 kilonewton is there, 300 kilonewton in the cable. Okay, and area of the cable is that 300 millimeters square. Okay, you need to calculate percentage loss of stress because of shrinkage, and that's the case is that if the beam is pre-tensioned beam, second case is that if the beam is post-tensioned beam, post-tensioned PSC beams. Okay, now it's also given that age of concrete at the transfer stage is equals to 8 days. So your T is equals to 8 days. That's the age of concrete at transfer stage. At the transfer stage is actually 8 days. Okay, let's talk about the first one, that's pre-tension beams. For the pre-tension beam, I would say loss of stress is actually equals to, because of the shrinkage, that is ECS into modulus of elasticity for the steel. You can take that ES equals to 210 kilonewton per millimeter square. And the value for the pre-tension is already that's the caudal provision value, that is 3 into 10 to the power minus 4. This is a strain, and we have some value of 210 kilonewton per millimeter square as the value of ES. So that loss of stress is coming to be 63 megapascals. 63 megapascal. Okay. And in the second case, yeah, we need to calculate actually the loss of stress percentage. So in terms of percentage, we have to calculate. Can you tell me what is the stress? Can you tell me what is the initial prestress because of these two? What is the initial prestress? P naught. That should be capital P naught divided by area of the cable. So that's actually 300 kilonewton by 3000 millimeters. So that is around 1000. 300 divided by 300 and into 1000. So that's 1000. That is 1000 megapascal. Initial value of stress is 1000 megapascal. So I would say percentage loss of pre-stress, that is 63 by 1000 into 100. That is 63%, I think. That is 6.3%. This is the percentage loss in the case of pre-tension beams. Now if I take that post tension, post tension, I would say loss of stress because of the shrinkage is 2 into 10 to the power minus 4 divided by log of 10, log to the base 10 into that log to the base 10 for your t plus 2, your value of t is 10, that your value of 10 is 8, your value of t is 8, such that log 10 to the base 10, that's 1. So your value is actually, this value is actually 1. So this part is actually 1. So into modulus of elasticity, that is 210 kilonewton per millimeter square. So final value of loss of stress would be 42, I think 42 megapascal, 42 megapascals. So based on that, I would say your percentage loss is actually 4.2%. 4.2%. Total, out of the total stress, initial pre-stress, you are losing 4.2% of the stress. 4.2%. That means the stress is more in this case pre-tension beam. So your shrinkage loss is more in the pre-tension beams, because your shrinkage is more in that one. Now one more kind of loss that we call as relaxation of steel. That we call as relaxation of steel. This is also time dependent. Relaxation of steel. This is generally, we take that this is 2 to 5% of the initial pre-stress of P0. This is almost 2 to 5% of initial pre-stress. So this is actually that phenomena, that is the decrease of stress. This decrease of stress under constant strain. So I would say the creep was the increase of strain at the constant stress, and this is the relaxation, is the decrease of stress at the constant strain. That's your relaxation of the steel. And this is a function of, I would say, your relaxation is a function of steel type. What is the kind of steel you are using, how much initial pre-stress you are applying, and what is the one more thing is there, what is the temperature? What is the temperature you are having in the steel wires? Your steel type means we have one term that we call as characteristic strength. Characteristic strength of that pre-stressing tendon, pre-stressing steel, we can write. So this characteristic strength for this steel, we write it as FP. So this relaxation is a function of some FP value. So that data is all it's a higher study. So we say that your strength, this what you call as relaxation loss, it is a function of FP, your characteristic strength of that steel, FP. Okay. Now its value is generally, we take directly that 2 to 5%. But actual value, it depends on the value of FP, and from that we do some interpolation, but we are not going to have any problem related to that. We are going to take general value that 2 to 5% of initial pre-stress, relaxation of steel. Okay. Now we are going to summarize that that final conclusions related to all those losses we have studied. Let's write that final conclusions about all those losses. Final conclusion. If I talk about the first one, that's elastic shortening. What is the equation for that? Elastic shortening of the concrete, because of concrete shortness in the elastic zone. So your loss of stress in the steel is actually that is M times Fc, and we can also say this is some average also sometimes. So this is M times Fc, and one more is there. Let's talk about friction loss. This is actually friction loss plus. This is actually friction, that is curvature effect, and one more effect was there, that's length effect, or that we will also say that is wave effect, or that is length effect, that is, we can also say that's wobble effect. So its equation was loss of stress is equals to initial pre-stress times kx plus mu alpha, and one more there was that was anchorage slip, and its equation was the loss of stress was because of the anchorage slip. That was how much is that slip strength, that is actually what is the total slip we have divided the total length into modulus of elasticity. So fourth one is that creep of concrete, that is the creep. We say that creep loss of stress because of the creep, that's actually m times fc, m times fc, and this was your actually, yeah, phi into m fc, yeah, 5 times, because of this creep coefficient, 5 times mfc. And one more is there, relaxation. Relaxation, that is, we take that as 2 to 5% of p naught. This is the total loss. So I think these are the six kinds of losses. 1 2 3 4 5. One more is there, some value is there. Shrinkage, yeah, shrinkage is also there. Shrinkage. So shrinkage loss is there. It's in the both pre and post. So that's loss. Loss equals to some strain, shrinkage strain into that modulus of elasticity. Now let's finalize that, which loss is happening in which kind of beam. So that I would write from this side losses, and from this side I would say, if this is happening in post tension, I would say that's tick. After that I would say that's if that is not true, so I would write false. Post tension, pre-tension. Post tension, pre-tension. Let's say that. Let's take the first case, that's elastic shortening. Let's talk about first one, that's elastic shortening. Elastic shortening. Is this possible in post tension? Yeah, because of the elastic shortening, I would say the loss of stress, I would say loss of stress, we are actually calculating loss of stress. Loss of stress is 0 if simultaneous tensioning and anchoring of all those wires, if simultaneously, but it would be 0. It would not be 0. It would not be 0 if separately, if we are tensioning one by one, if we are tensioning one by one, so that loss would not be 0. In this case I would say, so that means we can have the tick also, we can have cross also. There is both possibilities for the post tension, but for the pre-tension there's always that elastic shortening loss. And second kind of that loss, let's talk about anchorage slip. Let's talk about anchorage slip. Is this possible in post tension? Yeah, there is slip of that wire over the wedges, so this is possible. But in this case it is not possible for that post tension. For the pre-tension it's not possible. For the pre-tension it's not possible. And third one is there, that's we call as that's immediate. Yeah, that's friction loss. Friction loss, I would say this is 0 in what you call as it's 0 in pre-tension, but its value is there in the post tension. After that we have time dependent. Now first one is there, that's we call it as creep, and creep strain is both observed in post tension as well as pre-tension. So it's observed in both the kinds of beams. After that we have relaxation. Relaxation is also observed in both the kinds of. Yeah, we are not writing that. Why we are not writing that? I would say this is observed in both the kinds. Let's say this is observed in both the kinds. And after that we have one more, that's creep. We also got shrinkage. That's also possible in both the kinds, but we said that in the post tension we have lesser value of that, but in the pre-tension we have more value. So I would say it's observed in both the values, but this one is more and this one is lesser. So these are the final conclusions of those losses of the pre-stress concrete. Okay, losses of the pre-stress. Okay, now let's take the final problem that might be connecting all those. Yeah, let's take 2 final problems that would all connect all those dots related to the losses. So let's go to the first one. Let's take the first problem that we have to calculate stresses because of all those effects. So your problem is there, pre-tension beam is there, pre-tension member, pre-tension PSC beam of dimensions 250, 360, 250, 360. Okay, we have 8 wires. So let's say that there is some neutral axis, and from the soffit your wires are at 105 from the bottom. So somewhere here. We have how many number of bars? We have 10 wires, 10 number of bars of 8 millimeter diameter at this location. Let's represent that CG of that final bars. Let's say these are the bars at this location. So we have 10 number of bars of diameter 85 at this location. This is the location from the soffit. That is 105 millimeters. That is the CG of those wires. and that means the eccentricity from the neutral axis is equals to 180 minus 105, that is 75 millimeters. So your eccentricity is actually 75 millimeters. Okay, so your P force is applied here. So your P force is applied on this cross section such that your stress developed is equals to P by A, and one more stress is there, top tensile bottom compressor. So at this location, I would say, what is the stress? I would say at this location we have a stress of PE into E divided by I, and this is positive. Okay, let's talk about the problem. What the problem is saying all about? What the problem is all about? So initial pre-stress 1000 megapascals. Initial pre-stress in the cables 1000 megapascals. You need to say get the maximum stress in concrete. Get the maximum stress in concrete after transfer. At the level of steel wires. Steel wires. That means it's talking about get the value of FC. Okay. After that, we have to say calculate the losses. Losses because of elastic shortening. At the level of CG, we already know. At the level of those bars. Elastic shortening. Then after that, creep. Because of the creep, and creep coefficient is given to you as 1.6. Third one is there because of the shrinkage and because of relaxation. I would say in the pre-tension beams we have only 4 kinds of losses. Your friction loss is not there. Your anchorage slip is not there. So your only 4 kind of losses are possible in the pre-tension. That's elastic shortening, creep, shrinkage, relaxation. So let's calculate the final total loss. So let's calculate that. Okay. So first one is that we need to calculate the stress in the concrete at the level of steel wires. That's FC. Can you calculate FC based on this one? And we need to say what is the pre-stress force P0. What is the initial pre-stress force P0? So that P0 can be solved as area of the steel wires into the initial pre-stress we have. Initial pre-stress of 1000 megapascal we have. So 1000 megapascal into area of the steel wires. We have 10 number of bars of diameter 8. So this is your final P0 equals to 502.655 kilonewton. This is your P0. And area of the cross section of the concrete is also known to us. Your modulus of your modular ratio is also solved in this way. That modular ratio is given to you, that is 210 divided by 36.85. That is some value of 5.7. So this is modular ratio 5.7. And let's solve these values. So FC, this is the stress in the concrete at the level of steel wires. At this level we have to calculate. That's P by A, 502.655 newtons divided by area of the cross section 360 into 250 millimeters square. After that plus 502.655 into eccentricity square 75 square divided by moment of inertia, that's BDQ by 12. So you can solve these two values and your stress is equals to FC. That's coming to be equals to 8.50 megapascal. 8.50 megapascals. And now we want to calculate the losses. First one is that elastic shortening. What is the loss of stress in the steel wires at the level of steel wires because of elastic shortening? That's M times FC. So this is the first one. That's 48.45. That's 48.45 megapascals. And what is the stress that is remaining? What is the stress remaining out of the initial pre-stress? That is P0 minus 48.45. See, what is the difference here? I would say this one is actually immediate loss. Elastic shortening loss is immediate loss. After that, these three, they are time dependent. Losses. That means the remaining loss is equals to remaining stress in the steel wires is 951.55 megapascals. after elastic shortening has happened. Okay, now let's talk about the second kind of loss. That's the creep. What is the loss of stress because of the creep? Because of the creep, that's actually 5 times MFC. 5 times MFC. 5 times MFC. So let's substitute the values. Phi value has given to you 1.6. 1.6. M value 5.7. FC, what was the FC value? 8.50. 8.50. What is the total value we have? What is the total value we have now? What is the total value we have now? Is that 73.7? 73.7 megapascal. This is the loss because of the creep. Third one is that because of the shrinkage. Because of the shrinkage, there is loss of stress because of the shrinkage. What is the equation for that? If the beam is pretension beam, if the beam is pretension beam, we have that strain ECS. This is the ECS into modulus of elasticity. That is 210 kilonewton per millimeter square. So this is the equation for that. So that is 63 megapascals. 63 megapascals. So final loss is there. Relaxation because of the relaxation. Loss of stress because of the relaxation. What is the equation for that? That is generally 2 to 5%. That is 2 to 5% of P naught. Let's take the maximum value. That's 5%. That's 5% of P naught. Your initial pre-stress was 1000. So that's around 50 megapascals. 50 megapascals. That means we had to say what is the total loss of stress? What is the total loss of stress? Final value. That is the sum of all those. So 50 plus 63 plus 73.7 plus that one more value is there. 48.45. 48.45. That sum of all those comes to be 235.15 megapascals. And if I say what is the total percentage of loss? What is the total percentage of loss? That is 23.515 percentage. This is the total percentage of loss that we have in this case. Okay, let's take the final one. That's related to post-tension beams. Post-tension. This problem was related to pretension beams. Now we are taking the final problem. That's about the post-tension concrete beam. Post-tension concrete beams. Let's go for that. Let's take that. This is your post-tension beam. Post-tension beam is there. This is post-tension beam, PSC beam, and we have 3 cables. We have 3 cables. And we are jacking one end. One end is jacked. Jacking one end. Okay. We have 3 cables. 3 cables. One of the cable is that if we have a length of L, we have one of the cable that's in the form of that's bent cable. That's bent cable. That's having eccentricity. That's having eccentricity of E equals to 0 at the ends, and maximum eccentricity at the mid equals to 50 millimeters. So this is one of the cable we have. And one more cable is there. It's a parabolic variation. Parabolic variation with eccentricity equals to 0 at the ends, 0 and maximum at the mid, 50 millimeters. And one more cable is there. That's below the neutral axis at a distance of at some eccentricity E equals to 50 throughout the length. So we have 3 different cables. So variation of those is in this way. 3 different cables, and we have to calculate the total loss of stress. We have to calculate, finally I would say, calculate the loss of stress, calculate the percentage loss of stress, loss of stress in each cable, because of first one is there what you call as friction. One more is there because of elastic shortening. One more is there because of shrinkage. Because of relaxation. We have, and shrinkage strain is given to you, ECS, that is 2 into 10 power minus 4, and your value of phi is also given to you. That's 1.5. Your wave effect is also given to you. That we can say that's wave effect is also given to you. Wave effect. That's actually a wobble correction factor. 0.00 0.15 per meter. Mu value is also given to you. That's friction along the curve, 0.35. Molar ratio is also given to you, 200. That's 200 divided by 30. That's actually 2 into 10 power 5 megapascals divided by that 30 some value is there, units. So that is your M value. Okay. And it's also mentioned that all the cables are tensioned simultaneously. All the three cables are tensioned simultaneously. All the cables are tensioned simultaneously. Now, can you tell me what is the loss because of the elastic shortening? What is the loss because of elastic shortening now? What is the loss of stress because of elastic shortening? Because when we are tensioning all those simultaneously, simultaneous tensioning, is that loss equals to 0? Now I would say elastic shortening is this part is over. Now, because of the shrinkage, can you tell me what is the loss of stress in all those? In all those, I would say your shrinkage loss in all the wires because of shrinkage, that would be same. It's only a function of shrinkage strain into that value of modulus of elasticity. If the wires is a wire having same value of E, so I would say your shrinkage loss would be 2 into 10 power minus 4 into 210 kilonewton per millimeter square, and this is valid for all three wires, all three cables. So this shrinkage loss is coming to be 42 megapascal. 42 megapascal. Let's take this part that we call as relaxation. Relaxation, we say here we can take how much percent it has taken that. Let's take the 6% loss. Let's say the loss is 6%. Let's say that this is 6% of initial pre-stress P naught. So that is 6% of initial pre-stress P naught. Initial pre-stress of P naught, that was 1200 megapascals. So I would say total loss because of this in all the wires is equals to, how much is that? 72 megapascal. So this is one more loss we have. And what's left now? Yeah, only frictional part is left. So friction loss is a function of cable configuration. What is the shape, what is the orientation of the cable? Accordingly, your loss of the stress is going to be calculated. So if I say that this is your cable number 1, this is cable number 1, this is cable number 2, this is cable number 3. So I will calculate frictional losses in all those three cables. Frictional loss in cable number 1. So I would say this is your cable, and for that I would solve that your loss of stress is equals to P naught kx plus mu alpha. So I should know what should be the total length of the beam. So let's say that the total length of the beam, simply support beam, is L equals to 10 meters. And it was given to you that that we are jacking one end. That means one of the end is anchored and one of the side is jacked. Let's say this is your jacking end. So let's apply that pre-stress. So pre-stress of P naught. So I would say your loss would be now corresponding to this equation. P loss is equals to, what was the initial pre-stress? That was 1200 megapascals. Initial pre-stress was 1200 megapascals. Initial pre-stress. Yeah, it was given to you as initial pre-stress was 1200 megapascals. Let's write that. This was your initial pre-stress of 1200 megapascals. Into that kx, your k was given to you, your k value was given to you, 0.0015 per meter, 0.0015 per meter, into value of x. What is the value of x when only one end is jacked? At that time, I would say value of x is equals to value of length L, that is equals to 10 meters for this case. So 10 meters plus mu value. What is the mu value we have? That is the friction value, coefficient of friction, 0.35 into value of alpha. Can you tell me what is the alpha we have? What is the value of alpha we can take? If I say that we have this triangle, and there is some theta, and if I draw tangent, and here also we draw tangent, so this would be alpha equals to theta 1 plus theta 2. So such that your theta is actually tan theta, and we can say that is actually equals to E by L, E by 5. This is your E. E is your 50 millimeters, and divided by 5, that's L by 2 actually. Your 5 meters is 5,000 millimeters. So this is your value of theta. 50 by 5,000. 50 by 5,000 is your theta value. So let's substitute that. Let's substitute that alpha is 2 times of that theta. 2 times of that theta. Your theta was actually 50 millimeters divided by total 5,000 millimeters. 5,000 millimeters. So you just calculate that loss in the wire 1. That's coming to be 26.4 megapascal. So let's take the second case that we have a cable that's parabolic cable. For the parabolic cable, we need to calculate theta. What is the theta here? The theta is solved as tan inverse of 4h by L. Tan inverse of 4h by L, and that's tan inverse of 4 into h. H value is actually E1 plus E2, but your E1 is 0, so your E2 is actually 50 millimeters. So I will write 4 times 50 millimeters divided by length of L. Your length of L is 10 meters, so 10,000 millimeters. So this is your equation for theta. So that theta is coming to be, theta is coming out to be 0.02, and your alpha would be that cumulative angle between the two critical points. And when the end when only one end is jagged, at that time your alpha is theta 2 times theta, I would say theta 1 plus theta 2. So your alpha becomes 0.04. So let's use that 0.04 for the second case. That's your, in the second wire, your loss of stress because of the friction is kx plus mu alpha, and we have to use those values accordingly. So I had to substitute the values here. I would say in the wire 2, your loss of stress is equals to 1200 megapascal into 0.0015 into 10 meters plus 0.35 into your 0.04. This is the value of alpha here. Value of alpha. So this is coming to be 34.8 megapascal. Now, if I talk about the third one, if I talk about the third wire, that is a straight wire. Is there any curvature in the third wire? In the third wire, I would say curvature is 0. Your radius of radius is infinite, so I would say your curvature is 0. So your curvature is 0. So in that case, for the third wire, your equation is that P naught kx plus mu alpha, and this is the curvature effect. This is the curvature effect. That is 0 in this case, because it is a straight line. There is no curvature. Curvature is 0. That means curvature effect is 0. So only we have to calculate that change in position effect. That is length effect. This part is only, we say this is length effect, or this is what say change in position effect. That's a wobble effect, change in position effect. So we only need to calculate for the third one, P naught kx, P naught kx, P naught kx. That means loss of stress in the third wire is actually P naught into kx into x. X value is 10 meters. So this is your loss of stress in the third wire, 18 megapascals. Now, if we had to sum that, what is the total loss of stress in all those 3 wires? So in all those 3 wires, if I talk about the first wire, your loss of stress is one is your value of 72, one more value is 42, and because of the elastic shortening, we have 0 value, and because of this loss that we call as friction loss, so this was your 26.4. And if I talk about the second wire, your initial value that was same for all those 72, 42 plus 0. After that, your friction value is changing. Frictional loss is different. That is 34.8. This is the only difference in all these 3 wires. And for the third case also, we have 72 plus 42 plus 0 plus fourth one, that is because of the length effect. This value we have to take 18 megapascal. So you can sum the total values and you can get the total stress, and accordingly you can say what is the percentage loss of stress. I would say this is the end of the total losses we have. Thank you for watching our series related to that. Thank you for watching. Okay, thank you for watching. That is the end of these concepts. Thank you for watching these Prestress concrete systems.